A stone is projected horizontally from some height and another dropped simultaneously from the same height. They are on the same horizontal line to begin with. This is projected at some V0 and this is dropped at the same instant. You know what happens, right? Well, this falls straight down and will be half gt squared below its initial position, and this would also fall half gt squared from its initial position. Horizontally it would travel, say, at v0, but vertically there is no initial vertical component of velocity for the projected body, so it's going to fall half gt squared and they will collide. To collide, they must be at the same place at the same time. So this is arrived at this place. If this distance is d, this arrives at this position d by v0 later. That's the horizontal distance traveled is d and speed in that direction is v0. So this collision occurs d by v0 later and half gt squared below the initial position of the dropped body. Simple enough. So the body projected horizontally has fallen half gt squared, and this also has fallen half gt squared, and this collision occurs d by v0 after this is projected. Simple enough. Let me elaborate the earlier part, which I said is simple. Maybe it's not. So let's see. We projected body horizontally at v0, and on the same horizontal line as the velocity vector we have another body which was dropped simultaneously. Now if this distance between the two is say d, this was dropped and this was projected horizontally at the same time on the same horizontal line. So when would this projected body reach a position which is d away horizontally? That will be d by v0 later, right? And where would that be at that time? It will be half gt squared away. This is the vertical distance of this y displacement. Let's call this y-axis. This is y displacement, delta y, say. Half gt squared, and that is half g into d by v0 whole squared. That's where it would be. And where would this be at that time? The time of fall of this is same as time of horizontal travel of this, right? So this is arrived, this traveled a horizontal distance d and is half gt squared below the initial position. So whereas this also would be same half gt squared below, right? This would be half gt squared where time is the same. Since we dropped it at the same time as this was projected, time is same. So they both arrive at this place at the same time. This will arrive d by v0 after projection, and at that time this also would have reached the same position. So they have arrived at the same place at the same time and there is a collision. So regardless of the value of d, if d is large, well, time of travel would be larger. This would fall more, this would also fall more. The vertical positions of these two at any moment of time are same. The vertical position we are interested in is the position when the projected body has traveled that distance d, and this is the vertical position, this delta y below the initial position, and this also would be same vertical position. So no mystery there, they have to collide. What if the first stone is projected horizontally at say v1 0 and the second stone is projected simultaneously horizontally from the same height at say v2 0? Again, there will be a collision. Well, why would there be a collision? Because this would fall by half gt squared in time t and this would fall by half gt squared in time t, and since the vertical positions would be same, they would actually meet at a point below where they would have met in the absence of gravity. So, well, if this distance is d, they would have met at a time t equals d by v1 0 plus v2 0, and well, this is going to happen in the same time, but not at this position. It will be half gt squared below. So this would fall, and they would collide half gt squared below the point of projection. Well, the idea is that this would have the same vertical position at a given moment of time, but there will be, in addition, a horizontal travel. So they would collide half gt squared below where the initial height at a time given by this. So again, simple enough. What if we project something at V naught along a line, say towards some point here, and the stone projected at V naught at an angle, say theta naught to the horizontal, and this one is dropped at the same instant. Now interestingly, the collision happens again, mind you, both arrive at the same time at this position. This half gt squared below the point from where it was released, and this is the path traveled by the projectile. And well, this is not easy to see, but if you go vectorial, like for example, if you write the position of this particle, first particle, say displacement vector s1 bar is v naught bar t plus half g bar t squared. Well, this is the position of this particle. This, in fact, if you resolve this into two parts, v naught bar t would be this vector, v naught bar into t. So some t times this v naught bar, and half g bar t squared below that. So, and this is half g bar t squared, right? This half g bar t squared. So s2 bar, if you want to write, s2 bar is half g bar t squared. And what do you find? You'd find that, well, regardless of the distance between the two, there will be a collision, and this would occur when? Well, we'll find that time, but let's argue out this way. Let's not see this in terms of horizontal and vertical components for this projectile. We'll see it in terms of the vector v naught bar t plus half g bar t squared. So vertical position of this particle is half g bar t squared below that v naught bar t vector. Say, if this is a v naught bar t vector, half g bar t squared below, where t is the time they take to meet. And what is that time? There are two ways of dealing with it. One is to see it like this. This would have been, if this distance is d, say the horizontal distance between them is d, this would be d by cos theta naught. So the point here is that they meet, they collide below the point where, well, the collision would have occurred in the absence of gravity. In the absence of gravity, this would not have fallen. This would go and hit it here. So the collision occurs, well, in the same time, but not at this position. It is half g bar. That's what gravity does to these bodies. From the position where it would have been in the absence of gravity, it is half g bar t squared below. So this time is d by, this is d, right? This is d by cos theta naught by v naught. This is one way of seeing. Or another way of seeing could be, if this is d, the time taken to travel that horizontal distance d will be d by v naught cos theta naught. So this time can be also got as d by v naught cos theta naught. You can see they are the same. But there is something interesting in this way of seeing. You are kind of saying that gravity makes the body fall by half gt squared from the position where it would have been in the absence of gravity. So in the absence of gravity, sometime this would have reached here. This would not have fallen in the absence of gravity. So this has fallen half gt squared. This also has fallen half gt squared. Mind you, this dropped at the same time as this is projected. So there's going to be a collision, regardless of the distance. So that's what is interesting. So we're not going to analyze for position of this at so and so time and stuff like that. Looking at it this way makes it, well, simpler and also fun, I guess. Another interesting case is this. We project something at an angle to the horizontal, and from some distance away we'll project something else, some other stone say, along the same line simultaneously. And again, there is a collision. Interestingly, there is a collision. There is a collision, and this happens where? Half g bar t squared below the position where they would have met in the absence of gravity. Suppose this is v1 0 and this is v2 0 and this is d. They would have met d by v1 0 plus v2 0 later. That's when they would meet, but not here, half gt squared below. So again, what are we saying? Gravity is making them fall by half gt squared from the position where they would have been in the absence of gravity. So, well, again, if you write this S1 bar equals V1 0 bar t plus half g bar t squared, S2 bar is V2 0 bar plus half g bar t squared. And what is that half g bar t squared? This half g bar t squared, this is V1 0 t, this is V2 0 t. V2 0 times t will be parallel to V2 0, right? V1 0 t will be parallel to V1 0 and V2 0 t will be parallel to V2 0. So this is where they would have met in the absence of gravity, and now they're meeting here. So get this time this way and see it this way. That is, half g bar t squared gets added to that V1 0 t. That vector V1 0 t is this, and this V2 0 t, and this where they've met. A very elegant way of looking at the situation instead of splitting velocities into components and stuff like that. In other words, be vectorial sometimes. It helps. This is after all a vector equation. We split this into components, but we don't need to. Sometimes this is better this way.